So, hello together. Welcome to today's webinar. We're gonna have the third part of the RFEM 6 for students row. 2 weeks ago, you had the simply statics for members. Last week, you worked with our section on creating your own sections and importing them to RFEM. And finally, today we will go into surfaces and the finite element analysis in RFEM. So maybe before we start with the theory, me and my colleague will introduce ourselves. I'm Thomas Eichner, and I work for Dlubal like 1.5 years now. My main work here is the development of the dynamic add-ons. So everything within structural dynamics and the modal analysis, as well as earthquake design or machine-induced vibrations. That's all parts of my field. Also, I'm working in the customer support and help our customers with questions on the program. And yeah, today I'm your presenter. I'm gonna guide you through the theory, but mostly through the practical usage of the program. And with me there's Paul Sivolgin, and I think Paul can introduce himself.
Hello, also from my side. My name is Paul Sivolgin. I'm a working student at Dlubal Software, and I support the product development in the area of interfaces. So that's basically the data exchange between our software RFEM and other software like Rabbit, Tekla, Rhino, Grasshopper, Alplan. And yeah, and today I'm here to support Thomas and answer your questions in the chat.
Okay, thanks, Paul. So now we're gonna quit our webcams so you have more space for the presentation. And then we're just gonna start. So before we go into theory and into the program, you can see the GoToWebinar panel here. If you need more space for the presentation, there's this button on the top left side of the panel where you can minimize it. Also, if you have problems with audio or anything like that, I hope you don't have it, and if so, you can ask a question. We have this question field here below. You can use it for also for audio problems, but also for questions within the presentation. And in case you have the new GoToWebinar interface, which looks like this, there's the question button on the top side of this black window. And this is the place for your questions. So for today's guideline, we will do the part 3 of the series. It's the introductions into the finite element analysis, sometimes also called finite element method. And in the next 3 parts, so for the next 3 weeks, you will continue with the design chapters of the series. So with the steel design, the concrete design, and the timber design. For today's topic, we prepared a bit of theory, but you don't have to worry a lot because we don't go into depth in the theory. We want to help you understand the method and then just use it in the program with all its features. So this is what we firstly do. We will present you a reminder on the finite element analysis, continued by an simple example, a continuous lab with line supports as well as a area load. In the third part of this webinar, we will go into the plate theory. Again, it will be only in 2 slides, so not too detailed. Next, we will continue with the nonlinear calculations and the options in RFEM, and also how nonlinear calculations are carried out in our RFEM. Mostly it's done iterative, so it just needs multiple steps on calculations. And on the last point of today's webinar, we will have the singularities, which are a big problem within the finite element analysis, since they produce extraordinary high results which need to be treated in a special way. And we will also present you these special ways to treat the singularities. So let's start with the basic principles of the finite element analysis. And before I go into this, I have 2 questions for you. We will make a poll. And the first thing is just for me if you're working with 2 screens. So this helps me to know how many of you want to model along, because there are several models you can model with me. And if that's not the case, I will just go a bit faster. And also, if you want to repeat the webinar and model it in the future, this webinar will be recorded and also put online on our website as well as on YouTube. There are already some webinars on the same topic from the past years. Feel free to watch them if you want to, and you can also pause them at any time to model along. So now we have almost everyone participated in the poll. And for today, I think there's just one person that wants to model along and all the rest wants to just watch. So I will go in a midway. I will try for you to be able to model along, but I will also keep up a space. So let's continue with another poll. And this is about your previous knowledge on the topic. Have you already heard a lecture about the finite element analysis? So, okay, I give you like 10 more seconds. I think 2/3 already voted. And then let's see. So, a small majority have heard a lecture on finite element analysis already. So this will be a short reminder for you. And for the rest, I will introduce it to you and give you the basic principles of the finite element analysis. So then let's just start with the topic, the basics of the finite element analysis. Some of you may know from static courses in your studies that there are 2 methods on calculating static problems, mainly for overdetermined systems where there is just not a single way to solve the problem with an analytical solution. And these two methods are, on the one side, the force method, and on the other side, the displacement method. So the difference between those two is, in the force method, the forces are the unknowns. And in the displacement method, the displacements are the unknowns. So in case of the displacement method, for example, we have our equation systems with the stiffness matrix times the deformation vector equals the force vector. And now we have the unknowns in the displacement vector. So the target will be to calculate the displacements. The stiffness matrix can be constructed by using unit loads and then investigating the system on how this unit loads interact with all the degrees of freedom, with all the supports and with the internal forces. So the displacement method is mainly used by computer programs, and it's also used by RFEM 6, or in general by RFEM and RSTUB. And as I already said, the analytical solution for structures is hardly possible when it's go into well overdetermined systems, and therefore we need to decompose the structure into a mesh of finite interconnected elements. And with those elements, we can define properties in between each of those elements. So that would be the next step, that we define the properties at the intersection between the elements, which will be also called nodes in this chapter. And inside the elements, we can describe the mechanical behavior by approximation sets. And mainly for simplification, you could use linear approximation sets, but there are also, let's say, more complex approximation sets with higher order approximations, but that's maybe a bit too theoretical for now. We will just go with linear approximation sets in this case. Then one more point. This decomposing of the real structure into a mesh of finite elements, that's a so-called discretization. And a discretization is really like a big word in the topic. So it always helps to remember it, the decomposition of the structure into finite elements. And now we will go through a more visible procedure on how the finite element analysis calculation works. At first, we will have this determination of the local element stiffness relations. So we will decompose the structure, like here in point 1, into all these small finite elements. And in the second step, in the figure, we have, for example, here 2 of those finite elements. Please don't be confused. There are lines inside that could lead to like a more decomposition of the elements, but that's not the case. So these 2 here in the figure are the smallest elements, and you can just ignore the mesh inside them. So we have these small elements, and we have these properties between the elements. For example, it could be that the deformation in the z direction must be equal between those two, or the deformation in the x direction, and so on. Now we have the stiffness for each of those small elements, as well as the properties between those elements. So the next step would be to combine them. So we have our local element stiffness matrices. We also have our local element load vectors. And now we will transform them into a global coordinate system. And with this transformation, we can also put them all together into a global stiffness matrix. So we just combine the stiffness matrices of every single element into one global stiffness matrix. And we're doing the same with the local load vectors and combine them into the global load vector. So with this, we already have the stiffness matrix and the load vector from our equation of systems, which is stiffness matrix times displacement vector equals the force vector. And what's not known is the displacement vector now. And to be able to solve this equation of systems, we also need to take the supports into account. So in this step 4 here, we have now this green supports in the system, and we include them inside the displacement vector of our equation system. So for example, let's say this right side here, we have a completely line support, which means this line here can't move up or down. So we know the displacement at those supports must be 0. And that's what we introduce in our complete equation system into the displacement vector. So we can just set some of those entries to 0. When this is done, we're already ready to go and we can solve the equation system. So now we have all the deformations in the system, and with the known deformation, we can go into the post-processing for each single element and determine the support forces and the internal forces for each element. And this is then done by the approximations I already mentioned. And in this case, you can kind of see by the colors that there's more of a linear approach here. So it just changes gradually over the element. And with higher order approximations, you will get more exact results within these small elements. So maybe one additional information would be you can either decompose the system into more finite elements, or you could use more exact approximations of each element. That's like something we need to think about when we try to solve the system with a computer. Since with a computer, it's way faster to solve simple equations, such like linear approximations. And that's why we just use these simple approximations, and we prefer to decompose the system into more finite elements. Okay, so that's enough for the theory. And now we can just start with our example. This is what we will deal with in the next, I think, like 15 to 20 minutes. we will look at a continuous slab. The continuous slab will be loaded with an area load, just simply 10 kilonewtons per square meter. We will neglect the self-weight of the structure, so we will only have a loading of 10 kilonewtons per square meters. And then we will look at our decomposition, which is also shown here. You can see these white lines, which shows the these small finite elements. And we will do it in the program that we will use different sizes of these elements, and we will compare the results, and we will also compare those results to a simple beam. So for the ones who want to model along, that would be the time to open RFEM 6, because we're starting to model right away. And that's also what I'm gonna do now. We will go into RFEM 6. So I have a model open already, which we will look later on. And for now, we will go and create a new model. So this would be the button on the top left side of the program. And now we need to think about a name. For this name, I will go for 01 continuous slab. Now we have different options here. For me, it's always simple to use my downloads folder as a project name. I also have different folders where my projects are saved. But since I'm downloading a lot of models and they're always located in the downloads folder, I'm always going to use it as my main project folder. Next would be here. It's the type of model. Mostly we will use this 3D type model where you have the freedom to model along everything you want and consider every 6 degrees of freedom. But for our example right now, we can just use the 2D variant, which means we reduce our degrees of freedom from 6 to just 3. And we will only look a plate or in one plane constructed models. This also results in no solids possible, but solids will be treated in the future. So it's enough for us to just consider members and surfaces for now. When this is done, we can just initialize the model and we will have white screen, or some of you could have also a black background right here. That's something I always want to show, because for development, for example, I'm working with the black background since it's just more convenient for my eyes. And for presentations, I will always go with this white background. In case you want to change it, you could just go on to right click and then display properties. And here you could go for the background chapter just on top here, or just go for this box right on the left bottom side. Here I will use this white background, which is already loaded, so I don't need to change anything. We can confirm it and go into our system. What I will do next, I will delete every basic object in our system. Now I changed the model, that's not right. So now we're in our model again. And we can go with right click on basic objects and delete those basic objects. So whenever you create a new model, there will always be the basic objects of the last model overtaken. That's just for your convenience, that you don't have to create everything new in each model. So you can just use what you already constructed. And now we will go on and just model along. For me, it's way easier to look from a top angle view. And that means we go here on the top side of the program. We have the visibility, or let's say the viewing direction, which I will go for the Z direction. And yes, now we're ready to go. There are several options on modeling your structures. We have this data navigator on the left-hand side, which I think was already introduced in the first part of the series. And now we could go here and define a new material, and in the next step we could define a new section, and so on. So we could also create everything with just the data navigator. But since the speed of modeling is a very big point for workers, we also implemented these fast access buttons here on top. So these buttons make it easier with just a few clicks to create the system. And that's what we're gonna do now. So we're gonna do the create a surface element. We will create a simple rectangle surface. There it is. We can go with the presettings right now. The only thing we need to do is we need to create a new thickness. And a thickness is almost the same as a section, but it's way simpler since you only need to define one dimension, and this time the thickness. You could also use like varying thicknesses with different nodes and different thicknesses at each node, and in between this thickness is interpolated. But for today we will always go with this uniform thickness, which makes it way more convenient. So we will start with a model, and we'll start with a thickness of 300 millimeters. That's a typical thickness for reinforced concrete slabs. I worked in a testing bureau before, and I saw like everything between 200 and let's say 350. Okay, as soon as this is done, we can also see here we don't have a material yet, so we can just click on it, and the dialog for the material creation will open automatically. And now we will use a really nice feature, which is this book on the top right side here. Whenever a book appears in the program, there's a library where we have predefined values or predefined sections, or in this case, predefined materials. So it's just that you have it more convenient to just select, for example, a C3036, 3037, and every properties of this material will be overtaken automatically. So you could go and use those filters, for example, your region or the material type, if it's concrete or if it's timber and whatever. But what's way faster is if you know the material already, you could just type it in here and then select the material you want. For the C3037, there won't be much of a difference between the countries, but since I'm located in Germany, we will just go for this German concrete. So let's go for this here, concrete C3037, and press OK. And so we have the material, so we can also confirm it. And it was overtaken to the thickness, which we can also confirm. So now we are back in the dialog for the rectangular surface with the thickness as well as the material. And we can now confirm it and start the modeling. So for the slab, I want to have, let's see, 10 times 5 meter slab. So we will start at the origin, and then we will use our guide points for this finishing point of 10 times 5 meter. As soon as this is done, we have the slab, and I will rotate now a bit so you see it's just in one plane. So we don't see any thickness here. And that means that for us in the program, slabs are considered as planar elements. So they are just treated in one plane. In case you wanna visualize also the thickness, you could go for our visibility navigator, or it's called display navigator. So we go for the display navigator, and there will be the rendering chapter. On the rendering chapter, we have this model, and we can select the surfaces down here, and we can decide how they should be visualized. We can have them with the thickness, so now we don't have only a planar element, or we can also draw the contour lines of this whole system. So we're gonna stay with the filled option, since that's how the program also calculates the object. And now we can go back for the data navigator. So now we have our slab, and maybe you saw we want to have a continuous slab. So we will want to have line supports on each end of the slab, as well as in the middle of the slab. But as the line support name says, we need a line for the line support. So what we're gonna do is we just create a line with the help of this shortcut on the top left side of the program. We will use it, and we will take the midway of this top line. I canceled it. So just again, we will use this middle of the top line and draw it to the middle of the bottom line. And the program helps us because it gives us these nodes of, for example, the middle of this line. So we don't have to think about the coordinates or everything. We can just snap to those points and finish our line. Now we can go out of the dialogues via right click and go on with the loading of the system. For the loading, we will have a simple 10 kilonewton area force. So we will create this new surface load with the fast access bar on top. And we will use it just for this 10 kilonewtons per square meter. We will select the surface, confirm it, and that's where we have the 10 kilonewton per square meter now. So the last thing we need would be the supports of the system. So we will go into the bird view again. So this view in Z direction. We will select this line supports here on the left-hand side. And the predefined one is right for us now. However, I will go into this line support as well, since I want to show you something. And what we did in the start of the model, we picked our model type 2D for plates. And this makes it way more convenient, since also the support acknowledge this. And that means we don't have to care about all 6 degrees of freedoms. We only have the options to change the other 3 degrees of freedoms. So the open ones be faster, and this can make your work. So always think about your system and think about if it's not simply doable also in the 2D dimensions. So this support is just restrained in the translational Z direction, and so we can use it as it is predefined. We can confirm it and just select now our lines. As a reminder, if we drag from left to right, we will only take the objects which are inside our selection rectangle. If we go from right to left, we will have this blue rectangle, and this means every object are selected which intersect with this rectangle. And that's what we're going to do. And voila, now we have our supports in the system. So now the system would be ready to be calculated, but we want to interpret it further in further steps. So what we're gonna do, we're gonna select everything in this model, and we will go there with a right click, then on this manipulation, and then on move or copy. Also, this button could be reachable faster by taking just this shortcut on the top side of the menu. So within this copy modification, we can now define how many copies we want to create, or if we just want to move those objects. We want to copy them, and we want to have a total of 4 sets of those of the slab. So we will go and create 3 copies, and we will displace them like this is 10 meters. We will go 5 meters more, so we will go for 15 meters displacement in the X direction. And now I see we still have units of millimeters right here, which is not that convenient right now for me, and this is overtaken from another model for me, but the preset should be meters. So if you just created a new model, you should be fine. But in case you also have these millimeters right here, you can just go for this unit button here on the bottom left side, and there's also marked with this red arrow on which units we use in this dialog right now. So we are at the lengths, and we have here the unit of millimeters. We will change it to meters. Confirm it, and then also the dialog changes. Now we will go for this 15 meters and confirm the dialog. And now we have our 4 different slabs, but we don't have our guidelines, including every object. So, well, it's not necessary for the calculation, but I prefer to have our guidelines over the whole system. So we will go into a right click into our guidelines and object snap options, and there we will go for let's say a spacing of 0.5 meters instead, as well as I want to have in the plus direction, so to the right side of this x coordinate, we want to have 150 of those points. We will click OK, and now we have our new grid lines. So the next step would be to have a mesh refinement. So that's now about the discretization of the system. So how detailed each slab will be discretized in these finite elements. We also have global options. We won't use them here, but I'm just gonna show you where to find them. You can go for this calculate on the top left side, and then on the mesh settings. And now we can see in general, now the elements would be 0.5 meters in each direction. So this would be for all objects, but in our case, we want to have it different for each slab. So we are gonna use some property of the slab, which are also called types for surfaces in this case. So we have our surfaces, and those surfaces can have properties, and those can be defined in this types of surfaces section. So we will go here and go for this surface mesh refinements. Inside we can just go over it and go for 4 different mesh refinements. We can go for 2 meters, then create a new one. We will take 1 meter. We will take also 0.5. And then we will go for 0.1. Now we only have to assign those mesh refinements to our surfaces. This can be done with this top right side. We also have a button to select the surfaces. So we will go for it for the surface 1. Confirm it. And now see it's now assigned to surface 1. For the other 3 mesh refinements, well, it's simple for us since we have 4 surfaces. So we know this is surface 1, this is surface 2, and so on. So we can just go here and insert numbers manually. So now we're done, and each of those surfaces has a different mesh refinement. We have to confirm it. So in case you press the escape button now or cancel it, this create a surface mesh refinements wouldn't be saved. So always make sure to press either OK or apply. We will go for OK, and we will see the dimensions of this mesh refinements inside each slab. Now for result interpretation, we are also going with a simple slab. No, not a slab, I meant a member. So we will go for this new single member button. And now we're gonna need exactly, we're gonna need a new section for this member, and this can be done quite easy by just going into this create new section dialog. Right now we're gonna take the same material. We're gonna take the predefined section here, but we want to change the dimensions of the section. So we're going to go in the second tab, which is this parametric massive one. And we want to have now a width of 1000 millimeters, so 1 meter. And we want to have a height of 300 millimeters. So it's the same height as the slab, but it has a width of 1 meter, since all the internal forces and everything on the slab will be related to meter. So it will be always like kilonewton per meter, or yeah, exactly, kilonewton per meter. And so we're gonna use this 1 meter also for our member. We can confirm it and draw it right here on the right side of the last slab. We join it and just go for those 10 meters. And there it is. So we can go out of the dialog with the right click and treat this member now. What we're gonna do next is we wanna have also 2 supports on the end of the member, but we also want this 1 support in the middle of the member. But there's no node right now, so we need to split this member. And that's done by right-clicking on the member, selecting these member functions, and then say divide member by n intermediate nodes. So here we can have the pre-selections with 1. So it will just create a node in the middle and split this member. We also have another option to create an on-member node, which is quite helpful. That means the member won't be split into 2 members, but we will have a node on it to assign nodal loads or nodal supports. That's what we are gonna do. We're gonna create this on-member node and click OK. And now we can see this 1 node in the middle. With the pre-selections, these on-member nodes should be blue. So just to have a difference between normal nodes and on-member nodes. And now we can go on with the definition of our nodal supports. We will go into this nodal support, and this one seems okay. But one more problem, it also seems that no rotation is restrained right now. So we will go into this hinge. Since there's one more problem, this slab could rotate about its own axis, so about the x direction. So what we need is we're gonna restrain also the rotation about its own axis. And this is what we confirm. And now we can select our nodes with this button and just go for every node of the slab of the member. Confirm it, and there we are. Last thing to do would be the force, and this time we will go for 10 kilonewton per meter and select the slab to apply it. In case you did split this member, you would have to select both of the new members. So now we're almost done. I just remembered we also want to have a better comparison between the slab and the beam. So for this, we can go into the material. And in the material, there's this so-called Poisson's ratio. This Poisson's ratio means It's better explained later on, but simplified, it just means the interaction in, if like the four internal forces are moving in the x direction right now, it also impacts the internal forces in the y direction. And therefore it's, it would lead to more different results inside the slab than versus the beam. So what we want to do is we want to set this to 0. But for editing this field, we need to activate our user-defined material. And this enables us to modify everything in the material. So we can go for the Poisson's ratio and just set it to 0. When this is done, we can confirm the material. And we can go for a last thing, and that's a result section. So for the visibility of the results, we want to have a section in the middle of the slabs, which intersects every slab just in the middle. So we will find this these result sections just in the special objects of the data navigator. So we will go double click on the result section and then go with the predefined settings here. Means the section will be cut in Z direction, and we just have to define 2 points, which can be done with this button here. So I will go in the Z view again and just select the middle of the most left slab, and as a second point I will select the middle of the most right slab. Confirm it, and now we can see there's this section 1. Perfect. Now we're ready to go into our load case, which is just this self-weight load case. Per default, we always consider self-weight, at least in this self-weight load cases. So for us, we can just go and deactivate the self-weight, since we only want to have these 10 kilonewton per square meters or per meters for the beam to be considered. We can press calculate or first confirm it, and then calculate it. And I will just go for this show results. That means if we are clicking the show results button, we only want to see the results of our current selected load case or load combination. Means there's only one load case calculated, which can simplify or speed up our progress right here. So right now we see our different results for our different mesh refinements, and I will just go here on the top side. We can also select the same button for this show results to hide the results again. And now we can investigate a bit on the on our mesh refinement. And on the left side we had this 2 meters rectangle, and now we also see the constructed mesh right here. So we see there's only 3 elements on the left side. There's even a rectangle and triangle element, which should always be avoided. It's not always possible, but if possible, those elements should be avoided. Then in the next one, we would have 5 elements in between those line supports. And then it goes up to 10. And here, I don't know, could be about 100 elements between those 2 line supports. So, okay, let's go into the results. And in the top view, we just see the coloring of the surfaces. But if we go now for our minus y direction view, we're gonna see our results on the results section. So within those results, we will see some differences. But the program does not show us the values for each place here. So we will go for here on the left side on this result navigator. We will go for our result sections and then pick our local extremes. And now we have the values for each system. And we see we have 0.3 millimeters for this first very coarse mesh refinement. In comparison to our beam element with 0.5, which I just say right now it should be the exact solution. This is the solution we want to get with our slabs. So it seems like this is way off. This is way too coarse. Also, the next one here with 0.4 millimeter seems a bit off. For better visualization of the differences, we can also go for the internal forces. So what we're gonna do is we go for the member results right here. We will go for the internal forces and then for the moment about the y-axis here. So now we can see our my on the slab. Now we want to see the same thing for our other parts. That means we will go also for our surfaces. There we will go for our internal forces, and we will firstly, let's pick the my. And now there's something strange because the my, it's just not matching the results from our member on the right side. And there's a reason for that. That's the convention of the axis for slabs in comparison to beams. For this beam, it's kind of simple. We have our y axis of the coordinate system. It shows outside of the screen right now. And the my of the beam just rotates about this axis. For the slabs, it's a bit different. And now I will go into this mx. And this mx seems to be the thing we want to see right now. So for slabs, the mx means that in x direction, the slab is cut. And then the moment rotates about the corner of this cut. So that's the different convention for internal forces between slabs and members. So mostly for this system, it was quite simple since my can't be the same. So sometimes it just helps to click through all of those, at least in the beginning. And now we can interpret the results even more. Therefore, I will deselect the loads so they are not shown anymore. And now we see here 28.45 about these 31.18. Okay, that's quite a difference. I think that's almost 10%. And for the other ones, it seems quite better. At least this very fine mesh, it's almost the same as our beam results. So this is usable. Also this one, the difference is not even 1%, seems also usable. for me, also this one seems usable. Like the difference seems not that high. It's like 0.7 kilonewton meters, which would result in, I guess, like 1 or 1.5%. That's completely okay. But now we also want to see what's the difference in the location of this maximas. Because what we can see right now is we had 3 elements in the first slab. Can show it again, Z direction. You can see we have here 1, 2, 3 elements. And we also only have the results at the intersection of 2 elements. So what now, if, for example, in this case, the maximum would be in the middle of this, of this field. Then we could not have the maximum result with a coarse net. That's why we always need a fine enough a mesh for right results. And I learned in my studies, rule of thumb, that we would need 6 elements per span width. Means 6 elements between the line hinges, or 6 elements between a change of force. Let's say we would have a line force right here, and it would also be better to have 6 elements between this node and the line force. Okay, so that's all for this first introductory model right now. And now we can go on with a new poll. So one more thing as a kind of fazit of this whole mesh refinements. These finite elements should always be as fine as necessary and as coarse as possible. So as fine as necessary to achieve the exact enough results, but also as coarse as possible, because as you can see, we have 3 elements on the left side and we have, let's say, 1,000 elements on the right side. But that also means that the computational effort, and therefore the time the program takes to calculate it, is gonna increase by a lot. And for these small systems, it just wasn't visible in the calculation time. But if you imagine like a skyscraper with 10 stories, there could be really hours of differences, even days of differences, in dynamics at least. So, okay, then let's start. And let's say, do you remember what does the discretization mean in the finite element analysis? Okay, now we have a half of you have voted already. Let's give the rest like 15 more seconds. Okay, then let's close it. And yeah, the most of you were right. So the discretization means the decomposition of the structure into finite elements. Perfect. So let's just go on with another poll, which I just mentioned at the end. And it is the FE mesh size should be. And please pick the right answer. Yeah, okay. I saw one was very fast. I think he needed 1 second to answer this question. Maybe a bit too fast in this case. But yeah, then let's see about the results. And yeah, the finite element mesh size should be as fine as necessary, but as coarse as possible. So we want to have exact results or exact enough results. That means as fine as necessary. But we don't want to have too much calculation time. And that's meant by this as coarse as possible. Okay. Then let's go into our next two small theory slides. Because right now we're gonna talk about the plate theory. And no worries, this will be very simple and just related to the simple beam element analogy. So for beam elements, we have two types. We have on the one side the Bernoulli beam, and on the other side we have the Timoshenko beam. Well, for the Bernoulli beam, we have the cross sections which remain in the plane, and the cross sections remain perpendicular to the member axis. Also, we don't have a consideration of the shear deformations, and we have a rigid shear stiffness. On the other hand, we have the Timoshenko beam. And the main difference is that the cross sections don't remain perpendicular to the member axis. I will show this in a second. And we have a consideration of shear deformations, which means we will have bigger deformations due to shear than in the Bernoulli beam. Means we have this VBX, which is the deformation of the Bernoulli beam, plus this extra shear deformation. Also here this short comparison. For the Bernoulli beam, we also have this right angle between the axis of the beam and this section cut. But for the Timoshenko beam, we now have this shear angle introduced, which shifts our cross section now from our middle of the section. And for plate elements, it's almost completely the same. We have on the one side we have the Kirchhoff plate theory, and on the other side we have the Reissner-Mündlin theory. That means the Kirchhoff theory, it's geometrically linear with small deformations. Also the Reissner-Mündlin. We have the linear elastic material law of Hooke, also holds for both theories. We have the cross sections remain flat and there's no warping. And we have a constant thickness. And now the difference is the same as for the beam theories. For the Kirchhoff plate theory, we have the consideration, no consideration of the shear deformations. And for the Reissner-Mündlin theory, we have a consideration of these shear deformations, and additionally we also have the consideration of transverse and lateral strains, which means I shortly mentioned the Poisson's ratio before, and that's meant with this consideration of transverse lateral strains. That can be shown here. If we have a tension specimen, which is just pulled at both sides, then we would have, we could strike out this term mu times epsilon x for the Kirchhoff plate theory. But for the Reissner-Mindlin theory, we also have this Poisson's ratio inside, which means we will elongate this beam, and with this elongation we also have we have the section like getting smaller in width and breadth. So yes, so the cross section would shrink because of this elongation. Okay, then we can transfer it to the plate elements again, and there we had the simple mark of the Kirchhoff theory. It has no consideration of shear deformations. That's why it's called the theory of thin plates, because for thin plates we don't really need shear deformations because they are not big enough, kind of, and means we have the pure bending load bearing capacity. And all of these assumptions and these restrictions make it the simplified approach. On the other hand, we have this Reissner-Mindlin theory, which considers the shear deformation and is also called the theory of thick plates, but can also be used for thin plates. There's no problem in that. The component of the shear influence is higher, because the thicker the plate, the higher the influence of the shear. And well, that's, you consider the shear deformation, which means it's a higher value approach, and you get more accurate shear forces and deformations. So the Kirchhoff plate theory should be used or can be used for really thin plates. As soon as you have thicker plates, you should always go with the Reissner-Mindlin theory. In RFEM 6, the Reissner-Mindlin theory is the standard. So I will go into RFEM 6 for a short time again. And in the later praxis, you won't care about the difference between those theories. In fact, mostly you just use the preset, which is the higher value approach with the Reissner-Mindlin theory. But since you are studying all fields and all the theory, you could also need to use the Kirchhoff theory for comparing your hand calculations. And you could also use the Kirchhoff theory inside RFEM 6. And that's where you just go into your load case and into the static analysis settings. And inside this basic settings, you could choose between those two plate bending theories. So just in case you want to recalculate some exams or Okay. So now we could go for another short poll, and that would be this one. Is the following statement true or false? The Kirchhoff plate theory does not consider shear deformation. Oh, okay. I think more of the 2/3 voted already. And let's see for the right answer. And yeah, the right answer is writer, kind of. So most of you were right. That's pretty cool. And yeah, then we can just jump into our next topic. Now we are kind of through with this plate theory and with this theory of finite element analysis. And in the next models, we would go for nonlinear behavior. So whenever supports could, yeah, let's say, work differently for tension or for pressure, and so on. So we have it right here. Nonlinear calculations. The most important disadvantage of nonlinear calculations is that the superposition law is no longer available. Means you, in the studies, you sometimes calculated first the self-weight load case and then the live load case, and then you would just combine the results by adding them together. Yeah, there's a problem now since that's not longer possible. Let's say, for example, these typical applications in RFEM 6. We have the geometrically nonlinear calculation. So there's the first order calculation, and there's the second order and third order calculation. We go for, let's look at the second order for a second. It's also called P delta, consideration of P delta effects in English, quite a lot. And that means that a system is loaded and calculated. And imagine like a column which has point force in Z direction, so in direction of the column, but also a small horizontal load. And if you calculate this now, and you would get, let's say, a deformation of the top of this column of 1 centimeter. So this theory first order would stop at this result. So you would have the final result with this 1 centimeter displacement on top and with all the internal forces. For the second order analysis, which is the analysis on the deformed system, there would be another iteration. By means, we would first make this first order calculation and get this 1 centimeter deformation. Then we put the load on it again, but it already has this 1 centimeter deformation. And then we would solve for the equilibrium. So this 1 centimeter would result in 1.1 centimeter and so on. And we would do this again and again until the difference between two of those iterations is small enough. So along the second order analysis, you can imagine for each iteration you have a completely new calculation, and this demands computational power. So the more nonlinearities in the system, the longer it will calculate. So it's always on the engineer to think about what is even necessary for the system. And there are several guidelines in the different design codes, but for those guidelines you will have this next 3 parts of this series. So next step would be, or the next typical application area would be nonlinear material behavior. And one more nonlinearity that could occur is, for example, the nonlinear behavior of structural object elements, let's say members, hinges, supports, etc. So, for example, if you're in interaction between your geotechnics, your ground, and your structure, the ground will, let's say a building can stand on the ground, but the ground won't hold it back if the building wants to fly away. And that's also a nonlinearity, since the support would act differently in one direction than in the other direction. In general, these consideration of nonlinearities give more precise analysis, but it also increases the calculation effort. So that's why you try to not have many nonlinear stuff in your models or in your calculations if they are not necessary, because they are harder to interpret for engineers, and it's just more convenient to be in the linear range. So that's for the nonlinear theory and where they could occur. Now we can just jump into the program again. And now you don't need to model along. You can just watch for the next, I think, 4 models. After those 4 models, we will continue with 2 models again, where you can model along. So we will go for this one first. Right here, I will just delete those 2 stiffeners as well as those 2. And then we can go for the system. Right now, imagine a hall, and now we have it simplified in 2D. Means the 3D direction we just modeled by using those supports. We have overall completely hinged support, so those members could, if they're not holded, they could just rotate here around. Also on the top side we have so-called truss members, which means we can define the member type, beam or truss, and so on. I will go on this a bit later on. So we have here trusses. That means they are beams with hinges at each end. They can do only normal forces and don't take any moments. Means they could rotate here completely free. So right now we have the system, and now we have this wind load from the right side. And let's just try to calculate it. Okay, and it seems like there's an error. Let's see. Now we can have this table on the bottom side of the screen. We'll drag it up to see what is the problem here. And now it says us the stiffness matrix is singular. The structure is unstable, and that's at this marked point here in Y direction, so to the left and right side. Quite logical, since if we have this force here now, part of it goes on the bottom support, but also part of it goes on the top support. And now it pressures here from the right side, and the whole system would just rotate to the left and fall down. So that's a problem because the system is unstable. Now we will try to put in something to counteract this. And that's where we go for a nonlinear member. So what we're gonna do is we will create a new member here, which will be, in this case, we have either the tension members, or in our case, we will use now this truss member. So we see it here, we can only take normal forces. Okay, and a bit of shear we can also have, but we don't have any moment interaction. And now, since, let's take the section first. For sections, we want just a cable, which is only 20 millimeters in diameter. So we have 20 millimeters in diameter. And we have here, this length would be about 7 meters approximately. And when I think about it, if you now try to force this small 20 millimeters cable with pressure, it would just bend and go out of plane. So what we want, we don't want the cable to take pressure forces, because it can't handle it. It would just deform and not take them. So what we want here is we want a nonlinearity. And in the nonlinearity, we can say it's a failure if compression occurs. Also for member nonlinearities, just to show you, we have different possibilities. We could also go for yielding, or for, let's say, a slippage where first some deformation needs to occur and then it starts with the load bearing capacity. But for our case, we will just go with the failure if compression. So it can't take compression anymore. We will go for OK. And this is ready now. Just for your information, we have now defined this nonlinearity in the truss. We could do it the same way if we just pick this tension member right here. That would be exactly the same. So in RFEM, that's the positive thing. We always have like 5 to 6 options to make it right. So everyone can find his own way to model the structure he wants to model. Okay. So now we will go for OK, and I will go for two trusses right here, as well as 2 trusses right here. Okay, and let's see and calculate it again. Okay, and now we see we have here now the force, and I will also show the normal forces here. Let's go in this time the X visibility. Okay, now we can see we have here one beam. Maybe you can see it. This one is gray right now, and gray means this this member got deactivated since it got compression. It would have gotten compression, means now it doesn't do anything anymore. And these other 2 ones, those are on tension. So a positive normal force is tension, and a negative normal force would be compression. But now we have it. We have this, if we split this wind force into 2 point forces, it would be one on the bottom side, which goes directly into the support, and one on the top side. And this top side force would go this way, and then it would be held back, and then it's held by tension back to the support again. So yeah, that's for this example. Then let's just continue with the next one. And now we will go for this geometrical nonlinear stuff. Like we have this first order calculation and this calculation with p delta effects. So it's a simple system. We just have this this structure with we have a simple vertical loading, no horizontal loading right now. We have here a truss member. So again, you can it can't take any moment. And again, without those, this system could just fall to either side. But with those, which are now tension members, like it's almost the same system we had previously, but just one bay. And now we will go, and let me just look up. I will go for, let's do first this theory first order, so geometrically linear, and calculate it. And there we have it. We have great tension members, both ones, since we can go for the deformation in, let's say, the overall deformation. We can see it just goes downwards. It doesn't have any deformation in the horizontal axis. And within, or because it goes downwards right now, these members would need to shorten. And these members would need to take pressure forces. But they can't do it, so they will be deactivated. And now for the next step, we would have the theory second order. And for the theory second order, we always have a prescribed also horizontal deformation. So we will just go for it right now. Let's go in the second order. And I just wanna, okay, perfect, that's okay. We're gonna calculate it. Okay, and now we have the problem again. We have an instability in the x direction, because this pressure's down in the first iteration. Both of those members will be deactivated. Next iteration comes, it has a small horizontal deformation. That's from the p delta effects. The p delta effect always prescribes a small horizontal deformation, and then starts the calculation, but that's not working anymore since it's just gonna fall down. But there's an option for this, how we can calculate it anyway. Since the thing is, in reality, it could deform downwards, let's say, and even if there is a horizontal force, let's say, and it deforms to the right side, both got deactivated, but then there will be a point where this one member will not be under pressure anymore, but let's say it would be at this point where it is then, and then it would reactivate itself and take the tension, so the structure doesn't collapse. And this is something we can do within the static analysis settings, and it's called this reactivation tab. And here we can go for this exceptional handling and say failing members to be removed individually. So they are now not deactivated at the same time at once in one iteration, but first is only one deactivated, then it deforms further, and then the next one would be deactivated if it would be necessary again. In this case, it's gonna work now, okay, and deformed to the other side. That's okay, but now we have this one member active again, and only one of those did fail. So yeah, that's something about the geometrical nonlinearity and the p-delta effects and how to read them within RFEM. So I would say right now we are a bit over half of the time. So we could do a coffee break right now. Let's go for 10 minutes. And then we will meet up at 17:47 again. So see you then. So welcome back. So now we're gonna continue with our next nonlinearity. Right in the next model, we will look for support nonlinearities. Means I prepared a model for it right now. So we have here a cantilever, and on top of this cantilever we also have a beam. And in this first modeled object, we have just normal support, which has no nonlinearity and which is just fixed in the translational directions. Also, we have here, let's look at it in the wireframe model, we have here a nodal load on this point here of 15 kilonewtons. In the next model, we have exactly the same model, with only the difference that we now have a nonlinear support here. And within this support definition, let's go into it. We have said for this x direction, so in the direction of the load, that this support should fail in the case of negative forces in the x direction. And for comparison, I also did the same model again, but with the force from the other side. And now let's just look at this results. Let's calculate this in a second. Now we see we can also show us the support reactions here. In this case, we have this normal nodal support. We can see this horizontal force is mainly taken by this support. For our next model, where we said it should fail in case of negative px values, we have now the case that it is true. So the value px is negative, and that means that this support should fail. And that's perfectly inspectable right here. We now have all this horizontal force only be taken by this cantilever foot, and this support doesn't do anything. That means that this whole system will deform a lot on this top side. And in the third option, we have a positive px, which means this support won't fail and it will take all the forces. So that's a typical use case of nonlinearities for supports. It's the same also for hinges. Hinges and support nonlinearities are treated in the same way. And yeah, that's just a simple visualization of a null of a support nonlinearity. But let's go into a cooler example right now. That means we're gonna look at a ladder. Right now, we have this ladder, and this ladder leans against the wall. Means, let's see here, the support only acts in this X direction. So this ladder is held against the wall, and on the bottom side, it just stands on the ground. And now we try to model this standing on the ground. And this can be done, for example, with friction. And a friction is also, let's say, more complex nonlinearity than just a simple, okay, you don't work for positive forces. Because right now, we defined here for the X direction and the Y direction, this friction nonlinearity. And this friction nonlinearity is defined by this friction coefficient. Means the support can only take horizontal forces dependent on the force that is vertical to it. Means if we have 1 kilonewton here and we have a friction coefficient of 0.2, it could only take 0.2 kilonewton in this X direction. For support force of 0.5 kilonewton in Z direction, we could only take 0.1 kilonewton in the X direction. And now I try to simulate a single person of round about 100 kilograms, which equals 1 kilonewton. And I created here 16 load cases. We can also let us show this in an animation view. So we can see each load case changes the location of this person. So the person climbs the ladder. That's what we want to investigate right now. And now I'm gonna calculate all of those load cases. And we will see each load case can be calculated at the same time since they are distributed over all the processor cores. And what we also see is that from load case number 12, it won't work anymore. And now we will investigate why this happens. So we will go for the results and for the support reactions again. Now we are in the first ladder. Means we have this 1 kilonewton. We have 2 supports on the bottom side, and each support takes a vertical load of 0.5 kilonewton. So we had this friction coefficient of 0.2, which means with this 0.5 kilonewton in Z direction, the support can only take 0.1 kilonewton in the X direction. And now we have here 0.01 kilonewtons for the first ladder. Now we will go up the ladder and we will see this horizontal force will increase. This relies on the equilibrium of moments around this bottom point. And the farther we go away from this point, the higher this distance is for the moment calculation. And with this equilibrium, this results in higher horizontal forces the higher the person climbs the ladder. And now we can go upwards and upwards and upwards up to, I think, the ladder number 11 we are at now. Here we have 0.099 kilonewton. So it's beneath the capacity of this support. And if we go one step higher now, we are here now at 0.1 kilonewton in horizontal direction. That means the support can't handle it anymore, and the ladder would just shift away and the person would fall down. Okay, so that's no good for the person, but mostly the person could have a helper, right? So we could go, and now we will investigate the last one. So when the person is on the top side of the ladder, and now we want to investigate what happens if another person would go and stand on the last part of the ladder, on the first part of the ladder here. In addition, just to increase this vertical load. And this is something we could do by just going into our load cases. And now we will create a new load combination where we combine, let me see. Okay, where we combine these two load cases. On the one hand side, we have this person on the top of the ladder, and we will combine it with a person on the bottom of the ladder. We will go for OK. Then we will see here's our person 1 and here's our person 2. Now let's see if this works. Okay, and it seems like it's working. So now, why is it working? That's quite simple. We now have this horizontal force of 0.14, which is bigger than our previous limit of 0.1. But the difference is now we have 2 times this vertical force in total of 2 kilonewton. Means we also have the support reaction of 1 kilonewton per support. And we had this friction coefficient of 0.2. Means now the support can withstand 0.2 kilonewton of horizontal force. So now you know the static reason why it's always good to have some helper which holds the ladder on the bottom side or even stands just on the last spross of this ladder. Okay, then let's go into one more nonlinear example, which would be a tension specimen right here. And this is modeled as a surface. So we have here one surface with a thickness of 3 millimeter. And this steel specimen is completely holed on the left-hand side. See it here a bit in green. There the whole specimen is fixed. And we will go with our linear elastic material model first. And for the loading, we have here our 504 kilonewton per meter, which are applied to the right-hand side, to the free end of the specimen. So it's just a test example of a tension test where the specimen is just pulled on one side. Now this side of the specimen, so this one here, is 14 millimeters high, and in the middle we have a distance of 10 millimeters. So this here would be 10 millimeters. And we have a normal steel, so an S235, which means the yield limit of this material is 235 Newton per square meter. This force now is calculated. You can see it right here on the bottom side. It's calculated vice versa. We have taken this depth of, also the thickness of this specimen, so 3 millimeters times those 8 millimeters, times those 10 millimeters. We can see it right here. And those are now multiplied with our yielding limit, and with this calculation we result in our force, which is applied to these 14 millimeters line. So in the end this force equals exactly that this line here reaches the yielding limit of this steel. Maybe as a hint, if you want to calculate such stuff which is here in the comment, you could also use here inside this parameter, you could also go for formula and just go and create a formula yourself and let it calculate by the program. You could also use, for example, the thickness outside of our base data. So this could help a lot. And if you want to, let's say, geek out on this, you could just define here your complex formula and change even dimensions, and it would be overtaken automatically. Okay. So now in this load case, we have exactly the limit where the specimen is shortly, or it is at its yielding point. We also have another load case. This one is 503.5 and the next one is 505. So it's just a tiny bit more than this limit. And now we're going to investigate this on one hand with the linear material model, and on the other hand with a nonlinear material model. But let's start with this linear one. We will calculate it, and then we will look at the results of our exact limit state, this one here. Let's go for it. Then we see the steel, its limit is 235, but we are calculating with a linear elastic material model, which means it doesn't have a limit in this case. That means we have here our limit with this 235 Newton per square millimeter, but as you see, we have lots of stuff that exceeds this limit. But in reality, this wouldn't be possible. In reality, this steel would deform more. And that's what I also show you with this deformation. We have here our exact limit, so the first load case. We have a deformation of 0.1 millimeters. If we go now and increase the load a bit, we will stay at this 0.1 millimeter. Also for the forces, let's go on this. We now have just more parts of the model which exceed this 235 millimeter limit. Maybe just as a hint, also we see now this, all these boxes of the finite element. I can also show the mesh are now in one color. We can also adjust how the smoothing between those elements would be. And that could be done in calculate and then this results smoothing. So the standard settings of RFEM are this continuous within surfaces. And I will apply it. And then you can see it was just like, kind of averaged in between. And that's not the perfect way to go, since you have multiple results in one element. Means in case you investigate systems on a stress basis, it always helps to activate this constant on mesh elements option. We apply it, then we have exact values for each element, which is quite helpful for stress analysis. So we will continue with this result display, and in the next step we will change this material, and that's done by a double click on it, and then we will go for this isotropic plastic now, for the plastic material model. Let's see what it means to have a plastic material model. In here we can see, okay, we have the steel type, we picked our isotropic plastic material model, and we can investigate what it means. So here we have it. We have our bilinear curve. We have this initial stiffness with our E modulus, which is shown right here. The typical E modulus for steel, 210,000 Newton per square millimeter. And in our elastic model, this would be just going all the way up and never end. So for this plastic model, on the other hand, we now have a change in the stiffness as soon as this yielding stress is reached. And as soon as this yielding stress is reached, we have another stiffness, this EP, which is way lower, like 100,000 times lower than this initial stiffness, means it would need to deform far more to take more forces. It's also sometimes mentioned as strain hardening, means at this point the material can take more forces, but it needs lots of deformations for it. Then we can just go for it and calculate this one as well. So let's go. And there we are. So now we are again in this first limit case, in this first load case, which is where the material just reaches its yielding limit. And now we see here we have nothing really above. We have 1.12% of the overall elements. These are these in the middle ones, which exceed this yielding limit. So now it seems way more exact. We can also go and let's go with a double click here and say, oh, Okay, I did that already. I now limited my own like upper limits here. So I inserted here my customized limit for the top side, and that's right here. And we see 1.12% of the elements exceed this limit. If we put it the other way around, we would just not have the exact limit in it, and we couldn't interpret it right. So sometimes it helps to have user-defined limits in here for their result interpretation. So let's go back to it. Let's also look at the deformations. So now the deformation of 0.1 millimeter, we have the same deformation we had also with the elastic model. Okay, but what happens now with the stresses when we increase the loading? Now we're gonna look at this 1.12%. Now we went further, and now we see here in the middle 24% of all elements exceed this yielding limit, which means yeah, it just is in the second region of this bilinear part. And as I said already, the deformations are different now, since the second part needs way more deformations to take the load again. That's what we're gonna look at in our deformations now. With the linear elastic model, we had again this 0.1 millimeters, but with the plastic model, we now have 8.2 millimeters. So it's an increase of 820%. And one more good thing about this model is we can also, let's display it by animation. Now we can see it's just pulled out, and while pulling it out, it also shrinks here. So that's also a result of this plastic model and the equilibrium of volumina. So the volumina must be the same in the end. You can't create more volumen inside. So for the specimen to be able to take this more deformation, it also needs to deform in this Z direction in this case. Okay, so that's all about non-linearities for today. And for this, I also have another poll for you. So let's go for it. And now, please choose suitable examples for nonlinear calculation. And please, there can be more than one answer correct. So there will be more than one answer correct. And you can select multiple answers here. So okay, then let's go into the results of the poll. And now we see, okay, there are some answers, let's say. In general, all of those 4 options were correct. So kind of everyone was correct on some points. For example, the rods. So the members we had an example previously with those tension members, which are these non-linearities. For the materials, we just had the tension specimen. For the nodes and hinges, we had the example with this nonlinear support. And for the geometry and deformation, we had this theory of first order, geometrically linear calculation, as well as this theory of second order with the p-delta effects. So every 4 points can be nonlinearities. And every point increases the calculation time. And if you combine all of those together, you result in way higher calculation time. So always think about what is needed and what's not needed. Okay. Then let's go to our last part of this webinar, and that would be singularities. So what are singularities and where do they occur? General singularities are a phenomena of the finite element analysis, and those are points of discontinuity in the calculation model. This results in results which are not really usable or meaningful. The problem of singularities, in general, singularities are mathematical set values which tend to get to infinity. And those results are not usable. We can't work with infinities, right? We can't say, okay, we need this and this amount of steel in our reinforced concrete bar for an infinity amount of stresses. It's not possible. So, but in general, this is, luckily, it's only a model problem because of this finite element analysis, but it's not really occurring. So it's no physical phenomenon. And as I said, this can result in this infinite stresses and infinite internal forces. One more problem, and one big problem, is the mesh refinement, which we investigated in our first model, won't help to improve the results. It's more contradictory because if we refine the mesh, it could even make the singularities worse. Typical locations for such singularities are, for example, points and line loads, as well as point and line supports. Also, there can be openings or re-entrant corners. And in general, stiffness changes due to jump in material change or a jump in thickness. So if you imagine a point force, or I go into this within the next example, I would say. So let's go into RFEM again. And this is the point. If you want to, you can model along again within the next model, within the next 2 models. So we're gonna just create a new model for it. And this time we will call it, let's say, singularity of point force, or let's say nodal force. We can go again for our 2D plate model and initialize the model. Then we will now construct almost the same thing we did in the first model. by means we will create us a new rectangular surface. Now I have here predefined the steel material and thickness. Well, but that's not what I want right now. So let's just create a new thickness first. And this time we will say it will be 200 millimeters thick. And we will use, let's see, oh, not this one. We will create a new material because I want to use this, yeah, C3037 again. Let's take this one. Okay, just the same procedure we did in the first model. And we confirm it here. So let's check if it's all right. We have this 200 millimeters, the right material. Okay, then we can just start it and go from the origin to, let's say 8 times 6 meters. So this time we go a bit more quadratic, not exactly, but a bit more. Okay, now we have our surface. Now we want to have the location for the nodal load. And as the nodal load says we want to have a node where we want to have the nodal load. So we will put just a single node in the middle of our slab here. Okay, and done. So we have our node right in the middle. In the next step, we can go on and select our nodal load of 100 kilonewton. Then we can say OK and select our node in this middle. Okay, there it is. Let's look at it in 3D. Yeah, looks right. Let's go again in this top view and go on with our line supports. Now for the line support, I will just make it simple. I just take this preset hinged support, OK, and select all of those lines so that we have line supports everywhere. Okay, so that's done already, but we also want to investigate the mesh refinement again. So we will do the same as in the first model. We will copy it 3 times. Now I have the problem again with these millimeters. So I will go and change the millimeter unit to meters here with this unit button. And then we can go, and this time we will displace it by 10 meters. So there's always 2 meters between 2 of those models. We confirm it with OK, and yeah, there they are. And exactly this time I won't adjust this thing behind, but what we also could do, we could just not show it because we don't need it right now. We won't model more right now. So now we need the mesh refinement for the surfaces again. So we go for this types for surfaces and therefore the surface mesh refinements. This time I'll just go for this fast solution. I'm just gonna enter it, and the fast solution always has the danger to be too fast and input like wrong values. So, but now it looks right. Now we go for and put the first one to surface 1, second one surface 2, and so on. Okay, now we have all of this mesh refinements assigned. Click OK, and there are our rectangles again. And yeah, what's missing? Yeah, we need this special object again for this results. So we will take it and go for the special objects right here and create this result section. Again, the default settings are okay. We just need to select 2 points. So we take the middle one on the left side and the middle one on the right side. Confirm it, and there our section is. So we have the loading and everything, but what's missing is, well, what's still there is our self-weight. So we will go again on this top, on this load case definition, and there we will deactivate the self-weight again. And since it's no self-weight anymore, I will just call it nodal load. And yeah, we can just start the calculation right away. And now we will see something. Now we will see first the deformations. Let's go in our well-known -y view. Again, there are not all values. That's something I want to change. So let's go here for the result sections again and say this local extremes. Okay, this seems quite okay for the deformations, right? So we have almost the same deformations for each mesh refinement. But now what's about our moment? Let's look at our moment MX. Yeah, and there's something different. We now see we have 37 for this course net, 39, 45, so not too big of a difference, but a difference. And then at this fine case, we have 61. So we have here 30% more value than in this one. And now why is that so? Let's go into the top view again. Now we see, if we imagine now we have 100 kilonewtons, and now we just cut this 4 elements out, and we have to distribute this 100 kilonewton on these 4 edges, then we would have just like 100 kilonewtons divided by the length of this, the circumlength of this thing. And that's okay, but let's just assume 100 divided by 1, we would result in 100. But now we go smaller. Now we go smaller. And now we have less length to divide. So we would have this 100 kilonewton divided by, let's say, 0.1. And then it's kind of logical that we would have way higher stresses right here. And the smaller our elements would get, the closer this value would go to infinity. And that's a problem, because now we as engineers, we need to think about, should we take this value for the design, or should we take this value for the design, and what should we do? I mean, it could lead to 30% different in reinforcement, and that's something, that's worth something. It's real money, kind of. So we need to find a way to bring those results closer together and have a value we are okay with, we are financially okay with, and we are structurally okay with. So now we could go and do something inside our result section. And that's why I want to show you the result section itself. We can go inside it with, for example, right click and then result diagrams. And we could also reach it by this button on top here with this faster accessible button. I will go over this menu, just go in these result diagrams. And here we have it. We have the same results, just like without this 2 meter space in between. Exactly. So now we have it right here. And here we can help ourselves by smoothing them over an area. And that's what we're gonna do now. We're gonna go and select right here this edit smooth ranges of result diagrams. We have here, let's, okay, let me think for a second. In case we have here this point force, and we would estimate it to be on top of the slab. We can imagine no load is exactly a point load. It's always distributed somehow. Maybe it's a column that's standing on top, or even if the load is on top, it would then go in the concrete slab by a, let's say, 40-degree angle to the bottom, and so on. So it could distribute over a range around this point load. So now I would say it's simple. I would imagine a reinforced concrete slab, and for reinforced concrete, I always define the reinforcement over a meter. So the reinforcement we put into the concrete is the same for 1 meter width. And that's what I want to see here. I will smooth our results for a total of 1 meter. So this point here was 4 meters. So we will start at 3.5 meter and go to 4.5 meter. So we will do the same also for all the other locations. So this would be 11.5 for the second one, and 12.5. And for the third one, it would be 19.5 and 20.5. And the last one would be 27.5 and 28.5. Oh, okay. Every smoothing one is 1 meter. We can press OK. And now we see something interesting. Right here, all the values are quite, more similar now. And the most effect we have now for this fine mesh. Now it's vice versa. This fine mesh now has, on the average between this 1 meter, way less total moment than the other ones. So that's okay. We could use this for design. We could use this for design. In my opinion, I would go for this one here, because I love it to be on the safe side. Let's say it this way. So this one seems quite accurate for me. It's just for me a bit strange that this is way different than this one, but physically it's completely correct. So we could design it for this one, but let's say this 15%, I would say on this 1 meter, it's okay. That's not too much waste of money. Okay, so that would be one possibility. We could insert these moving ranges. We could also print this window into our printout report or directly on a paper. And yeah, then we could use this one for the design. Okay, so let's go out of this again, because there's another possibility for treating those nodal loads. And I will create a new load case now. And I will call it nodal load area load. Press OK. And what I'm gonna do now is, as I said previously, this 100 kilonewton, there won't be a needle with 100 kilonewton punching on the slab. So mostly it will be a column, for example. Let's say we have a column of 0.5 times 0.5 meters. Okay, that's a big column, but let's say we have a 50 centimeter times 50 centimeter column. So what we could do is just transform this load into an equivalent area load. That's what we're gonna do now. So we delete this nodal load. Then we will go for a free surface load in this case. Exactly, and here, yeah, let's take the free rectangular load. And now we can put in basic settings here. That's okay, the direction is okay. It should work in Z direction. We won't have this complex of a system. We will just have, let's see, just this system. We can always switch between this explanation and our model right here. We will define it with a center and the sides of the rectangle. So we want to have here 0.5 meter side lengths of this column. And we want to select the center point of the first one and select the surface of the first one. Okay, and now I will help myself. I won't exit this dialog with OK, but this is now a good example on why we have these apply buttons and so on. We can now press apply and next. Almost. I forgot the load itself. We had 100 kilonewton. Let's do it with a formula. 100 divided by 0.5 divided by 0.5. Apply. Apply, and then we have here 0.01. Why do we have 0.01? The thing, our formulas always work with the SI units. So in this case, this would be Newton and meter. So this wouldn't be Newton in this case, but kilonewton. But we can help ourselves and just edit this kilonewton here, I think. Divided by 0.5 meters and meters. And I thought it would work, but it's not right now. I think we would need, let's go here. Now this is for object properties. Okay, I will do it differently in this time because I'm not quite sure how to insert the units right now. I will just go for 100 kilonewton is 100,000 newtons. Apply. Why isn't it working right now? Now we have it. Okay, I did a mistake with the commas. Okay, I won't try it with the units again, but I think we could also just insert the units as I did in the first step, but we need to use points instead of commas here. Okay, but yeah, now we are with our 400 kilonewton per square meters, which is equal to our point force of 100 kilonewton. And now the good thing with this apply and next, we can just apply it. We can see the load appearing, and then we can just select the next center point, the next surface, and say apply next, and do this for every surface right now. Doesn't matter if we select the surface first or if we select the center node first. That's just how you prefer it. So let's go here and here. The last one I will quit with OK. Now we can calculate it again and see how this helps our singularities. Here we are. Just gonna go in the results. Okay, there's something off right now. Maybe I did something wrong in the modeling, but let's directly go into our results section. Okay, that's a bit strange right here. I'm gonna investigate it further later on. But what we see here is now that the results are way more similar than in the first case. And also now we have here a smaller result, a smaller maximum than right here, for example. And that's something we can think about. If we would smooth it again, you see here there are more points here beneath, and here it's just a triangular distribution. Means this here diminishes faster, and if we integrate now, like with how we did it before with this result smoothing, we would estimate to that this one would increase compared to this one. So we could combine also these two methods. We could use first this area load instead of the point load, and then we could also smooth it out. That would be like the the most exact solution in this case of these three solutions, and could help out. Depends on how exact you want your results, or okay, that's it for this model. And now we will start our last model together. It's gonna be kind of similar. It's gonna be also about the singularities. So we will start it by initializing the new model. And this time it will be called Singularity Nodal Support. Again, in this 2D dimensions. Let's initialize it. Okay, I have this already. Let's add some numbers. And there we are. So it would be almost the same procedure first as in the previous two models. Means we will construct us a few 4 slabs with different mesh refinements, and that's what we're gonna do right away. So we will go for a new rectangular surface. We will go for thickness of a new one of 300 millimeters. Let's see, we want to have this concrete C3037 and okay. Let's look at it in the bird view and go from the origin to, let's say 8 times 4 meters. Yeah, 8 times 4 meters. Let's see, this one looks okay. Now we will add a line support to the right side. That's also okay for us. And then we want to have a nodal support. And I want to have this nodal support to be right here. So let's go for a node first at that place. And then directly we could go for a nodal supports assignment. But this time I will try it in a different way. We will go into the node itself and just say, okay, I want to have a support there. Go to support, and then I will select this hinged one. That's just a different way to model a nodal support. Okay, that's done right here. What's missing is our loading again. So we will go for our surface load and we will just pick 10 kilonewton per square meter again. So let's go for 10 here on that surface. Okay. And ready to copy it. So let's mark everything we did already and copy it again like 3 times. Let's displace it, I think 10 meters. Yes, it's again 8 meters long, so it should start at each line here. So let's displace it by 10 meters. Okay, there it is. I will just again deactivate or disable our grid here. Oh well, let's try another thing with the grid. We see it stops right here, but we can adjust the grid in our workplane options. And this time we can say we don't want to care about, just do it for me and put it around my existing model. We're gonna do this, and that's what we get here. We don't need it anymore, but just for you how to go for this option. Okay, next thing would be missing is the surface mesh refinements, as well as the section result section. So let's start with the surface mesh refinements right here. We're gonna go from 2, 1, 0.5 and 0.1, and we will just go with the surfaces 1, 2, 3 and 4. Okay, So let's go for it. There they are. And last thing to do would be this result section. So we go for the special objects right here. And just select again this leftist node, or this leftist midpoint, and this rightist midpoint, and confirm it. There it is. And now we're ready to go. Or, well, I want to deactivate the save weight again, so we only have 10 kilonewton per square meter. It's always better for interpretation. Okay, and yeah, let's just start calculating. Like, if we wouldn't deactivate the save weight, it would just be, I think, 30 centimeters times 25 kilonewton per square meters more. So I think around about 6 to 8 kilonewton per square meter more, but with 10, that's a smoother value, I would say. And there we are. We can also look at it on this way. So for the deformations, yeah, now we see the one point I said earlier in this model. For example, you see we have here the maximum of 1.4, and it would get larger until here, like you see in the most right model. But we don't have a value here because we won't calculate it here. That's why we need enough elements for, in between each support or load definition differences. Okay, but that seems quite similar, at least between those three. But again, like in the previous model, the internal forces could make the difference. And there is the difference. So now we see here, even with this modeling, there's even a jump. So we can't use something like this course. It's just not right. And then we see with the finer the mesh gets, the finer the higher the results get. And it's kind of the same reason as for the nodal load, because you could just interpret it as this. Let's activate the support reactions. They are the same. You could just interpret this support singularity as if there was a nodal load from the bottom side. So it almost is the same. We could also do this results moving right now, same option, but for nodal supports we have one more option, and that is we could define, on the one hand, we could define here in the nodal support an elasticity. Like we could go for this here, then say we could go for 7,000 kilonewton per meter. Yeah, let's just try it. Now we see we have here a spring displayed, which means it's elastic. We can calculate it again. But in this special system, it won't help us out because this system is kind of static determinant. Let's see here. Yeah, we have kind of the same values as before. And if we now look for the deformations, we have differences because this support just goes downwards as well. So why didn't this help? Quite easy. We have a static determined system. So that means it's hold here, and if either of these supports wouldn't be there, the system wouldn't work anymore. That's kind of why it's static determined. And the problem is now, even if we have here our elasticity, the forces don't care, because the forces have to go somewhere, and they have to go into this nodal support. So with the force, the way where the forces go, there's nothing changing, and that's why it does not help in this case. For static overdetermined systems, this would help, because if you model it that way, the forces would go to another support, and that's why, the forces would decrease in the support even. But since it does not help right here, we could also go for another option, and that would be inside this nodal support again. We can go now and say we have, what are those supports? In general, we would have a wall underneath the slab or a column underneath the slab. And that's what we could do here. That's this button. We could define the stiffness of this support with the help of our imaginary column. So let's go for this one. We see we have the support on all places. So it will tell us, so this image always helps us where the support is active. And while activating this stiffness via fixtures column, we will get a new tab here on top. So we can go here and then we can define the column beneath. Right now this is okay. We say it's 0.5 times 0.5 meter. We can say it's hinged at the base. Okay, we don't want it to be steel. We want it to be concrete as well. And now we want to have a height of 3 meters. And all of these values come into place for this spring definition. Okay, so maybe you did learn in your studies already, you could always go for equivalent stiffnesses instead of the modeling the column itself. And that's what's done here. And one more thing which is changed is we won't have a pure nodal support here. What we will have is, like here, we will have like a surface support instead. And that's we're gonna look at the results now. Let's go for it here and here, and just look at the last results for today. And there we are. We're gonna just jump into our mix again, and there we see we now don't have results inside this column, because for those calculations, almost always this moment at the end of the column is important for the design. So here this is spared out, this region, and now we see, okay, it got better. We had here like over 100, now we are at 47. That's way better for the design, but I think I would go with the result smoothing anyway, also in this case. So there are several options for treating with singularities, but you always need to be cautious with singularities and not just trust completely in the values that a program gives you. So maybe in the end, what we did today, we talked about the finite element analysis, about the principles of the finite element analysis, and also how different element sizes can impact the results. Also, we looked at it in RFEM itself and looked through the modeling process of different mesh sizes and the investigation on the impact of the mesh size on the results. We also did look at different nonlinear calculations, as well as the final part of the singularities. So how singularities occur and how we can treat them right. So for the end, I just want to give you a hint on our website. Since, let's see, right here. Since the whole program is free for you, so companies pay a lot to use this tool, and for you it is completely free, and you can recalculate your exams, or maybe for some exams there are no, let's say, no solutions given. So with this program you could just model the exam question into RFEM, and with the right checks there you can get your completely right solution to check your hand calculation. This will also be very useful in the upcoming events. There will be the reinforced concrete and all the design modules, and we implemented something to show you the whole process of each check. So that means you can directly compare your hand calculation with each step with the program results. And exactly, so here on our website, on the let's go for the English one. In the education chapter, we can have here students and schools, and here would be this free structural software for students. That's the way where you can get this software. Also, you could go and use RFEM 6 for your thesis. And in the case you submit this thesis, you would also get a $50 Amazon voucher, as well as a license for after your studies for free, which is quite perfect. That's a few $1,000s you can kind of get there if you're working right after you study with this program, kind of, or if you want to use it. Also, we have this downloads and infos portal right here, where you can find several examples, and also you can find several manuals and our whole let's say knowledge base, which can be found, I think, right here in the support and learning chapter. We have here several knowledge bases where, for example, the theory second order can be studied and shown within the program. And I think that's all. I hope it wasn't too exhausting today, but hope you enjoyed it. And maybe just for you, we can show our webcam for saying goodbye for today. And Paul, was there any question open in the end?
No, everything is cleared and answered.
Okay, perfect. Then it would be perfect. After the webinar, there will be a short poll for you on how you experience this webinar. So please take part on it. It's like a Google review. It's 1 is the worst thing to say and 5 is the best thing to say. So keep that in mind and have a nice evening. So bye.